Hello, welcome everyone to this presentation about object storage for cloud-native applications, mainly focusing on object storage in a Kubernetes environment. My name is Nicolas Trangez. I work as a principal architect at Scality, and I'm joined by Vianney Rancurel, who is also an architect and our head of research, also at Scality. This presentation is split in two pieces. In the beginning, I will focus on what is cloud native, a little bit on what is object storage, what is Kubernetes, what is the landscape of storage within Kubernetes right now, both storage products using Kubernetes as well as consuming storage from Kubernetes-based workloads. And then later on, Vianney will dive deeper into a new technology, a new specification API, so you want, called COSI, the Container Object Storage Interface, which is a way to integrate object storage or provisioning of object storage in a Kubernetes cluster and with Kubernetes workloads. We start off with something very basic. This is a storage conference, so all of us know about storage, object storage, etc. Just to lay the grounds and kind of explain how we perceive object storage, Scality being one of the big object storage vendors. So object storage as a storage paradigm is quite unlike the more traditional file and block storage. Object storage is inherently unstructured. It doesn't give you any type of directories, for example, even though you can, of course, emulate those in key names. It is hence non-hierarchical. All the objects are kind of self-contained. There is no such thing as a symlink or a hard link or references to other objects. Of course, in your higher up data model, you can build that yourself. But in the storage, from the storage systems point of view, there is no such thing. And everything you store are uniquely identified blobs with some metadata. And this is where an object store differs from, for example, a plain key value store. Think memcached or Redis, where you have a key that points to a value, an arbitrary blob of data. In an object store, it's important to realize how metadata is an inherent feature of the object store system. There's various consistency models. Like everyone knows, Amazon S3 initially was eventually consistent, even though nowadays they are strongly consistent. And depending on your application, being strongly consistent is more important. Of course, being eventually or relaxing consistency guarantees may allow for a larger scale. In most object storage solutions or most object storage APIs, objects are collected in so-called buckets. Buckets, containers, various vendors use different names for kind of the same concept. But within a bucket, the namespace is flat. So objects are, again, not structured. There is no hierarchy between objects. Access to an object storage system is at the object level and is very often nowadays through HTTP RESTful APIs, even though there are non-HTTP and even non-TCP based access methods to object storage as well, but those are not really in use that much. An example of such an API, being SNIA, is the CDMI API as well. Most object storage solutions or environments give you fine-grained authentication and authorization towards either buckets, objects, what you can do with objects. Very often this is policy driven, so this goes beyond the traditional Unix model in the file sphere of access control, and especially in block storage world where it is very binary, either you have access or you don't have access. In the object storage systems initially were very create, read, update, delete based, even though I should have removed the update part, because you cannot really update an object. You can only overwrite an object with a new blob. So assigning a new blob to the original key. But nowadays, object stores, they come with features like versioning, where for a particular key of an object or name of an object, you can have multiple versions when you updated the object, not really in place. There's CRR, which allows you to cross-site replicate objects from one site to another for high availability. There are features like metadata search, which allows you to query the object store and return to you a list of objects that match a particular search in the metadata that goes with the objects. There are APIs to do server-side queries into the payload Think, for example, S3 Select, which is not unlike metadata search, really looks at the blob itself and allows you to extract information out of that blob on the server side. Historically, object storage was perceived as being slow, even though most systems had very high throughput, but also latency was rather high. But nowadays, object store is also fast. It still has the high throughput as before, of course, but nowadays, object storage systems also give you low and, more importantly, predictable latency, which allows for new types of workloads, more kind of transactional style workloads, which were not really possible before. I think definitely in the AI and ML world. Can we continue with cloud native applications? What is a cloud native application and what are the architectural principles that underlie cloud native applications? So this is a quote from Joe Beda, who's the co-founder of the Kubernetes project and of Heptio, which was a startup in the Kubernetes sphere, nowadays working at VMware. Cloud native is, it's an idea. It is not something that you can translate into an architecture just like that. It is really about how you structure your teams, how teams collaborate, the technology you use, pervasive automation all across your, not only your application stack, but also your infrastructure stack, and bringing those together. So this relates a lot to the DevOps movement. And then various architectural principles or guidelines, or even get pushed into various architectural principles, which manage complexity and really unlock velocity to build features quickly for your end customers, hence building a lot of value easily. What underpins cloud native architectures? Primarily, it's about everything being rather loosely coupled and service or contract oriented. This goes into the microservices way of working, where you don't have this one monolith sitting on one server doing a lot of tasks. No, instead you split this up into multiple pieces which each run independently and communicate, of course, but they run independently and they can be developed independently as well. For example, by multiple teams or using multiple frameworks, etc. An important aspect of cloud native architectures is that automation is really pervasive. Everything is API driven. You don't have an admin go into some server to install some package and then start a service. No, all of this should be automated, be it using traditional tools like Ansible or SaltStack, or nowadays using, for example, container orchestration on Kubernetes. Cloud native architectures, it also relates to some principles which help you to design scalable software. Scalable in multiple dimensions, in performance and business growth, in engineering teams, both the size of a single team as well as scaling out into multiple teams, all working on the same product. And of course, in the ability to deliver features to your customers. One architectural paradigm is a clear distinction between stateful and stateless services. Stateless services themselves, like inside of them being stateless, they can of course communicate with a service that is stateful, think a database or an object store, really contributes to the performance scalability. When services are stateless and are split from this monolith, the traditional monolith, it really allows you to scale out your application and hence handle higher performance needs. Going with the pervasive automation, cloud native applications tend to consume technologies as a service. You don't deploy a database with your application consumes a database as a service and through some API says, I want a database to be provisioned and managed for me. This can be either literally in the cloud, on Amazon, on Microsoft Azure, on Google Cloud or others, but it can also be on premises where application developers nowadays look for cloud-like experiences, which can then be provided by the in-house infrastructure team or external vendors. This goes for databases, storage systems, big data, AI, ML pipelines, whatnot. But again, all of this very API and automation driven, which is where COSI, which Vianney will talk about later, definitely comes in. In a cloud native architecture, you try to have no or not too many so-called pets. Pets are special servers or special applications which require constant care, which need to be available. We really aim for the cattle approach, which is this term used for You just run a bunch of those services. None of them is really special. If one of them goes away because a node dies, then you just run it elsewhere. You don't want to have any special places within your architecture. And last but not least, cloud native architectures are often also portable. It allows you to port your software quite easily from one environment to another. It doesn't mean it's write once, run anywhere. But for example, containers help you to be able to move your cloud native application from an on-premises environment to a similar in the cloud environment, or the other way around. A little bit on Kubernetes as a container orchestration system. Really just from a very, very high level, what is Kubernetes? And looking at it from an architectural point of view, or from an architect's point of view, not from a user or a system administrator point of view. But these topics are kind of important to understand why COSI, which again Vianney will talk about later, is designed the way it is and works the way it does. Kubernetes in essence exists out of a consistent, highly available database called etcd, which is based on the Raft consensus protocol, which is a bit like the Paxos protocol. You have a cluster of servers, like 3 or 5 of them, and then based on a majority, a quorum, new keys and values can be stored in this database, and you're sure that even if one, or depending on how big your service set is, if a couple of the nodes within your cluster die for whatever reason, your data set is still available. Next to that, Kubernetes defines a data model, an extensible data model using so-called custom resource definitions for objects that can be stored in that database. This is very abstract, but most of the objects, the types that are defined, are rather abstract by themselves as well. And last but not least, Kubernetes provides a RESTful API to create, read, update, delete, and important, watch objects. With watch, I mean watch the creation of new objects, deletion of objects, updates to existing objects, etc. Why is this object model so important? Because Kubernetes is intent-based, it is declarative. You don't go to a Kubernetes cluster and you say, run this container on that node. Instead, you say, I want to have, in a so-called deployment, 5 instances of this container to be running, and they should share some storage that should be provisioned for them as well. So that is my intent. That is why I express in this desired model of your application. And then Kubernetes has all the things that are needed to actually realize that in the real world. So for starters, there are many so-called controllers in a Kubernetes cluster, which watch for creations, updates, deletes of these objects, the higher level objects I was referring to before. And then they can create, if applicable, or again, update, delete, and read, of course, other objects, most likely lower level objects they refine to get more things done eventually. And then also update the status of the watched objects such that you as a user can really see whether a controller is making progress into realizing your desired state of affairs. Sometimes some of these controllers can also call into external systems in an imperative way. So as an example, when using CSI, the container storage interface, a Kubernetes will call into, or could call, depending on the architecture of the storage system, into a CSI driver to then create, provision a volume in an external storage system, which is a declarative, which is an imperative call, or delete a volume when it is no longer required, which is again an imperative call into the backing storage system. Finally, to realize all of this in the real world on particular nodes, servers in your cluster, and there's a bunch of agents that run on your various servers in the cluster. First and foremost, there is Kubelet, which is really the working horse of a Kubernetes cluster. It sets up container networking by calling into so-called CNI plugins. CNI stands for the Container Networking Interface. A couple of implementations of those are, for example, Calico or Cilium, which really set up cluster-wide networking. Kubelet can call into storage, into storage drivers, for example, through the container storage interface, to set up node local require things to access storage from a container. And then finally, of course, kubelet can start, stop, monitor containers through the so-called container runtime interface, the CRI, of which containerd and cryo are possible implementations. Next to that, on the Kubernetes node, there is a service called kubeproxy, which is running. That one is in charge to set up IP tables or IPVS rules to set up in-cluster virtual IPs for services. I won't go into details, but kubeproxy is really responsible to set up networking at the host level, not across hosts. And then finally, some CNI implementations, for example, Calico, also require a host level daemon that sits on every node in your cluster to set up routing rules and a couple of IP table rules as well. So what we did at Scality is we built a storage service, a storage product that runs on Kubernetes. So we really embraced the cloud native paradigm and cloud native technologies in our storage products. Why did we do so? Kubernetes and the cloud native paradigms principles that it kind of forces you into, it's not really forcing, it is really gently guiding you towards, allows you to build really scalable software. Kubernetes itself gives you a lot of functionality primitives to build this larger scale software. And if you, or to manage this software at larger scale in production. But it also, given the split between stateless services, etc., guides you towards designing your applications such that it becomes scalable. This then goes into the loose coupling and the portability, which allows us to take the same product, the same technologies, the same software, the same containers, and really run it in various types of environments. Currently, we don't support it in any kind of Kubernetes environment, but from a developer point of view, for example, this portability is really useful. So what does Kubernetes, next to the cloud native principles, it kind of guides you towards? What does it bring? It's got built-in cluster management. You really have this whole set of nodes, servers, like tens, even hundreds of them in your cluster, and Kubernetes really gives you a lot of principles, or not principles, mechanism to manage your cluster. It can help you to automate deployment, which, remember, is a very important aspect of cloud native software, through so-called operators, which are like controllers to deploy and manage the lifecycle of a particular piece of software, a particular technology, a particular product. Kubernetes really manages the whole stack. Containers, you can manage the operating system through Kubernetes with some extensions. The eventual application, you can unify operational tooling, including things like Prometheus for monitoring and Grafana for graphing, to really monitor the whole stack in one environment. Unlike virtual machines, Kubernetes, when using it with containers, has a minimal performance impact, like disk access, networking, because it's simply using Linux namespaces and C groups. The performance impact is rather limited. But as a drawback, Kubernetes has limited support for non-cloud environments. You really feel as a user or as a deployer how it was built for cloud environments where things as a service are available. Disks as a service, virtual networks as a service, virtual machines as a service, which you don't have for on-premises bare metal environments, which is where Scality is deploying, or where we are deploying our products. So our journey to Kubernetes really started end of 2017, beginning of 2018, with a new project back then called Zenko, which is our open source multi-cloud data controller. This was presented by Vianney back in 2019 at SDC as well. And Zenko is really a set of services, microservices, both stateful ones as well as stateless ones, which you can deploy or which are deployed on a Kubernetes cluster. Because customers want to also run this on premises, we built our own Kubernetes distribution called MetalKates. It's also open source, so you can go on GitHub and find it there. Zenko itself is open source as well, which is really tailored for on-premises physical machine deployment. I presented this also at SEC in 2019, so take a look at the recording or the slides of that session. And finally, and this is from 2021, we announced the Artesca product, which is really built as an object storage solution for the cloud native era, also embracing Kubernetes. Very, very quickly, I'm out of time. And I'll just leave it to Vianney to talk about COSI, which is really a way to work with object store in a Kubernetes environment. Thank you.